All right, hello. So this is Warren McAvoy, Professor McAvoy, and I would like to introduce kind of the idea of some of the core cryptographic primitives that are used sort of repeatedly in this Bitcoin protocol, and mentioned in the book. And obviously not getting into details, but I'd like to try to draw some analogies to perhaps help you understand how this could work. So a little bit of just core words in cryptography. So there's the idea of encrypting something. So the idea of encryption is to take some item, a document that's in plain text, and then essentially transform it in a way that, with sort of a physical space sort of analogy, it's as if you put it in a safe, and then the encryption step is to put it in the safe. So this is encrypting. Sorry. And then the act of taking it out of the safe is decryption. So there's two main ways in which encryption and decryption happen in the world of cryptography. One is called symmetric key, and one is called a public-private key pair. So they're symmetric, and then public-private. So start with symmetric key. A lot of the primitives that are used in the protocol really come up from this sort of style of encryption. And so you just sort of create the physical computation. Actually, when you think about history of computation, really cryptography in this sense drove computation long before anything else. If you look at maybe an introduction to computer science book, I believe they might say the Jacquard loom was the first example of a programmable device. It was a loom that knitted different patterns depending on what holes were punched into a card. But really, the lock, which was done many centuries before, so the Jacquard loom was in the early history of the United States. The idea of a lock is something that goes back to early history, which is sort of an indication of just how important the idea of controlling access to things is part of the structure of society. So let me just show you what a basic tumbler lock is from a mechanical point of view, and this is sort of a good analogy of what symmetric key encryption is like. So as a mechanical access device or computing device, the way a typical tumbler lock works is there's this barrel. This is where the key is inserted. So the key goes into here. And then inside of this barrel, there's a number of holes that are drilled. And then inside of those holes, there are basically, and the holes continue into the case on the other side. So when it's all lined up, they all just pass through this way. So let's say there's that many of them. And then pins are inserted. They're actually pairs of pins into these holes. And they're actually pairs, they're sliced at different locations. So they're not all the same, but they're actually a pair of pins here, a pair here. And then there's a small spring in each one of these. Like this. Okay, so now these are not aligned, and so therefore this cannot turn with respect to the housing if they're not aligned. And what the key does is the bumps in the key are different heights. That's the highest one and not as high. Basically, when you insert the proper key, it lifts these pins so that they're all aligned with the tumbler, like this. And in that way, once they're all aligned, then you can turn the tumbler, and that allows whatever mechanism this is attached to release, all right? So it's actually one of the first examples of mechanical computation. It's programmable in the sense that you have to just, if you can extract the tumbler, which you can once you can actually unlock the system, you just have to change the cut marks on this, and then a different key would open the lock, all right? And so by having the key, you have access to the tumbler, and then this becomes an analogy of an encryption scheme, is if you think of a safe that has such a key in it, right? So you have a safe, and there's a door, right? And that door has such a lock on it that uses this key to access it. Well, so to encrypt something would be to use, this is the key here, and in this sort of system, there's the single door with the single style of key. But anybody with an access to a duplicate of this key or a duplicate could then open this door and essentially encrypt and decrypt, right? So encrypt would be to add a message into this, and to decrypt is to take something out. And so this is a good analogy to the digital version of this, which I might introduce in a next video. I just want to create the analogies now for what they do. But basically the idea is some message could be outside of this, right? And then by applying the symmetric key, you can put it inside of something where it is not accessible. Maybe, I guess, to carry an analogy, you can kind of weigh this thing to find out there's something in it. If you encrypt something, you still have data, you just can't tell what the data means until you apply the key again to recover it from back into its original state. So, so again, this is a symmetric key encryption. And then to take things out of the safe is decryption. And really, in the terms of the history of civilization, this probably represents one of the first instances of a sort of computation. It was a specific tool to solve a problem, this encryption problem, or this hiding of secret problem. But this was an important enough thing that it actually happened about 600 BC, were the first analogies about 600 BC is roughly the times that you start seeing these devices. And they, of course, might have existed long before then, but we just have no recovery or no archaeological evidence of those kinds of devices. So symmetric keys as physical computation, physical devices have existed over the history of secrets and ciphers. So let me try to do this in a more like messagey way. So if you had a symmetric key idea, and this isn't a great key or a great way to keep a secret, but I'm just trying to draw analogies for you. So imagine you had a secret which you put on a transparent like piece of plastic. And so you had a message or an image or something like that that said, you know, sleep tonight or something. I have no idea. Okay, some message, right, was written on this thing. So if you had a device, for example, that very precisely and in a repeatable way took this message, say, and just cut it up into smaller pieces, like this. And then, according to some systematic table, and this would be the key, so according to some key, each one of these pieces would be, say, switched to a new location in the same grid, and then perhaps rotated in some way. So this one will move there, and this one will move there, right? And maybe this one goes down here, but it's flipped upside down. So, oops, I guess upside down means it's pointing up this way, like that. So the key in this case would be the choice about, well, for this little grid mark here, where would it go over here, and then what action happens? And the idea is if somebody had that key of actions, right, then this would effectively be the symmetric key here. And so if you had access to the key, it would be a very, well, depending on the problem, you could take an image, translate it into something that perhaps, again, it's not a perfect example of encryption, but I hope you think that if you did this step, it would be much harder to decipher what this thing meant than just looking at the original image. And so this could be a version of symmetric key that would take a message, turn it into a comparable, like sized message, right? It doesn't really change its size at all. And whatever way you could transport this thing, you could transport this thing via the same mechanism, right? This fits in an envelope, and so does this one. And once, if the person, either you or some other person has access to the same key, they can then either have a machine that would do this for them, or just carefully undo the steps and then recover the original image. So again, this would be sort of a mechanical analogy of how you could create a symmetric key, where you could, I think, imagine building a machine that if you gave it the right rules about how to do the transformations, you could program different keys and it would do different translations into this, and you would end up with an image or a new document that then was essentially encrypted. I mean, not as strong as modern encryption schemes work, and then you could decrypt it in the same way. So I guess a digital analogy of this is data is represented as zeros and ones in binary, so you could imagine this sort of as a grid of zeros and ones. Doesn't really make sense to flip a 0 or 1 since they always look like a 0 or 1 if you did it like as an image, but flipping in that case might be to always switch certain zeros to ones according to some key. And then that would allow you to take a patch of zeros and ones and turn it into a different patch of zeros and ones, where if you knew where they all moved to and you knew all the changes that would happen from those zeros and ones, you could take a pattern of zeros and ones here to a pattern of zeros and ones here that would be much harder to understand or to decipher what the original meaning was without the key. But then with the key, you could carefully undo those same steps and restore the original data. So that's called a symmetric key, and is a common tool. And there are the modern versions of that, the kinds of things that are used for both Bitcoin and for other encryption schemes that you use all the time now, without even thinking about it. Every security connection you make to different devices are employing encryption schemes that are vastly superior from a mathematical, theoretical point of view, but strongly analogous to this that I just said. So there's symmetric key, all right? So a couple of analogies. So then what about this one? What's about a public-private key? So let me go back to the original mechanical analog. So a good example of that is, so you have the same sort of safe idea, all right? So there's a door and there's a key for that door, and we'll call that the private key on that side. So things that are in the safe, if you have access to the private key, you can, I guess you can both insert or extract using the private key because you have the private key. But then what you can introduce into this system is, say, I think this is not terrible as an analogy, like a little secure door, drawer with a hinge that the bottom falls out like this. And then on this side, there's a key that accesses this drawer. So on this side, you can open the drawer. If you have this key, you can open this drawer and take a message and put it in, and then close the drawer and take the key out, right? And now the message has fallen down into here, right? So once you put it in here, you can no longer retrieve it, right? As you put it in, it's in the private space now, so it's not retrievable here. And so this side is called a public key over here. So the public key is how you put the messages in, okay? And then the private key is a way to get the messages out. And so this has a bunch of uses and what? And it's quite hard to move from this analogy to like the gridded example. Like, what would you do that you could do a scheme to this that would be analogous that anybody with this piece of information could get this far, right? But then nobody, then afterwards you couldn't get anywhere else without having the private key as well. Like if you do a step that involves just the public key that locks it somehow in a way that you now need a secret that you didn't have to reverse it. And I'll just say, it is a hard mathematical problem that was solved, I guess, relatively recently in a cryptographic sense, I believe about in the 60s. And it has to do with, there's a couple of analogies or a couple of ways of doing this now. But basically, there's a mathematical transformation you can do where if you have a certain piece of information, you can do a transformation that results in something that then you cannot undo. If all you have is this piece of information, obviously anybody could photocopy the original before they put it in here, and that's true analogously in digital information. You could keep the secret and just encrypt a copy and leave it there. But if all you have is the encrypted copy and you no longer have the original, then in this public-private key world, this analogy actually works. It takes a document, digital document, transforms it into another digital document, which effectively, using just the public key information, creates a new document that is not recoverable unless you have a different secret, which is called a private key, and they're related to each other, but I don't think that's that important in this case. Unless you have the private key, and then if you do have the private key, then you can take this document and recover the original. So this is a physical lockbox sort of analogy. I think is a very good analogy of how public-private keys work. But unlike the symmetric key kind of idea, where I think it's pretty easy to see what you might do to create that sort of structure, it is a mathematically interesting change in the world when somebody sort of understood what could be done to make that happen. And the mathematics of that, you look up, it's an interesting sort of part of the world of cryptography. But for this class, I think the important part is to understand this as an analogy. So public keys allow you to encrypt things in a way that you could give this to all kinds of people that maybe you don't trust to read the document later, right? But if they have access to the public key, then they can use that to create these documents, which then, after they are created, only the recipient can do something with it. And that's an important concept in the sort of idea of cryptography that we've discussed multiple times, but sort of never try to draw too much of an analogy about what those things might be. So symmetric key, a public-private key. The next one that I think is important to talk about is something called a hash. So what? So these have to do with encryption. But then we talk about this thing called a hash. And what is that? So I think in the real world, hashes are a lot harder to give examples of in the safe sort of version. But I think up here I can give you an example. All right. So again, this is not a great version of a hash compared to the cryptographic hashes that are available now, but I think it's a good analogy of how this might work. So how would I do this? So imagine that if you had an image, same kind of idea, and you did the same thing that we did for the symmetric key problem, where you chopped it into little squares like this. And then you had a key. And the odd thing about this is now this is a key that everybody knows. It's actually not a secret. So it's not secret, which is weird, right? So and then you do that thing where, I don't know, they all get moved to a different, sorry, not zeros and ones, but like P's and Q's and things like that. They all get moved around in this image, right? And you get this new image that's all mixed up because of the keys where certain values are moved to different ones, and some of them are, say, rotated or something like that. It's an image, all right? So, of course, that's not very secret at all, right? Because if the key is public, then anybody could just reverse this and get back to the original image, all right? So now let's do something else, and we'll have a second, and again, this is a publicly known step, but now we're going to combine the information and say stack all the rows on top of each other. So this gets stacked on that, and on that, and that, right? So these get stacked, and you get this sort of tall little pile of images. They're all partially transparent. Remember, we started with an image that was on like a transparency, so you can see through it. So then you do this transformation, and then you collect these in the same order. You take the first one on top of the second one and the third one, and then make a stack, right? So here's your little stack this way. And then do the same in the second row all the way through to the last row, right? So you take what was a grid of data, and you get down to a smaller set of data, all right? And then instead of sharing this publicly, okay, you then shine like a bright light through all of this and record the resulting image. So you take this resulting image, and it turns into this sort of really weird set of things in here all the way through here, okay? So you can take this image and do this transformation, and then do this compression step where you take all, from here to here, you have the same amount of information. So this turns into the same amount of stuff. But now you summarize it into what's called a digest. This is called a digest. Sorry, I mean, last step here. When it's all put together, that's the, you can't see that corner. This thing is called the digest. And so what's interesting about that is, okay, so you didn't, if you had a message and you said, I know something that you don't know, and everybody knew what these rules were, including the particular transformations that you do in order to do this, then you could do these steps, right? And then produce this digest, and then like put this out here somewhere. It's like, here's a thing. And so what's interesting about that is it helps prove that you know something. Because if later on someone said, oh, well, you made that up later, like you said you knew something, but in fact you didn't. Well, I hope you see it. It'd be really hard to just start from one of these. If that's the only information you had was the digest on this side, it'd be pretty hard to figure out, like, what would I draw over here so that when I do these steps, I end up with a certain digest. Like if someone gave me the correct document, then I just do the steps and I look at it, like, oh yeah, those are the same. So the digest, it somehow is a proof that you knew what this document was. But if I'm wrong, right, if I change a letter in this thing, right, by the time I finish these steps, it will have changed the image in some way and it would look different. And so it would become essentially a hard problem to figure out, well, if someone told me later on I had this someone told me I had a digest that proved that I knew something, and then you wanted to create something after the fact, like after someone published this digest, you want to find something that makes it up. You probably have to try quite a bit of futzing in the image to end up with a message here that once you did these transformations, you'd end up with a digest. So what's cool about this, and the mathematical versions of these are very strong, So in the end, there's a digital analogies to these, where in the end you get a signature or a digest on this side that any change here substantially changes the signature on this side. But if you give it exactly the same, the binary equivalent, exactly the same document on this side, you do the steps of the hash, and you'll get exactly the same digest on the other side. So the idea is going this way is easy. So for a computer, in case of things like the SHA hashes and that sort of stuff, there's a fairly easy set of steps that it can go through from the point of view of a computer to do these transformations and come up with a sequence of bits on this side that represents this digest idea. But if all I have is the digest and I'd like to go back and recover the original image, that is like really hard. So, you know, in this analogy, maybe there's some trickery that you could, find small changes and figure out where they go to. The mathematical versions of hashes that people use in cryptography, it is a tremendously hard problem to know this. If all you know is this, then going back is hard. And so the idea of a digest is a tool that can essentially summarize a document down to something that you could put publicly, which in the end, you can later use to prove that you had the original document, because otherwise you couldn't come up with this thing, without actually revealing any interesting information about this document, all right? And so that's the idea of a hash. So the hash, the idea is a document goes through the hash, and you get a digest on the other side. And the digest is somehow, it's a lot smaller usually. So whatever hashes are designed computationally, no matter what size document on this side, you get the same size digest on the other side. So the SHA hashes that we're talking about, they're all of a certain bit length by the time it's all done. And so you take the document, you hash that document, it gives you a digest on the other side. And so later on, if you wanted to prove that this document was the same, you just take the hash of that document and apply the same hash, and you'll say, well, see, I got the same hash again, so this must have been the original document. But someone else who only had the digest could not find any document. There'd be it's a computationally very difficult problem to find either the original document or any other document, even if it was not the original document, that you could apply the hash to and recover the original digest. So again, this is easy, and then this is hard. So if you find the same one, that's recovering. If you're trying to find another one, if you're trying to find a different document that has the same digest, that's called a collision. If there's two different documents that have the same hash, then recovering one of those two different documents is called finding a collision. And so it's hard to find any document, whether it's the correct one or the incorrect one, that has a matching hash. And this is super crucial in this whole blockchain business, that basically these digests summarize a vast amount of information. So these documents can be quite long, and then a single hash can, from this long document, show quickly that you knew what that was. And if you know the digest again, it would be very hard to either create the original document or some forgery of a different document that just happened to be true, that if you use the same hash, you get to the same digest. So there are some of the core, what are called cryptographic primitives, at least analogies for them, that we will end up talking about next, and are alluded to in the text and some of the discussions we've had in class so far. So it seems useful to try to be a little more concrete about what they are. All right, thank you very much.